that down a bit. Probably only like barely hear me, but that's okay. I haven't slept, so that's fun. Okay. So what did I say? What I was gonna? Okay. My lovely presentation. The way that I organized this was based on the TEKs provided in the last year's assessment. So that's what this is going to be based off of. It's going to include questions from previous STAR tests, including the one from 2018, 2017, and 2016. Varied questions from there. And we'll be going over the material there, hopefully. And this is how it's going to go, just TEK, and then we'll go into a question about it, and that's how we'll do that, hopefully. So TEK 8.5a, describe the structure of atoms, and including the masses, electrical charges, location of protons and neutrons in the nucleus, and electrons in the electron cloud. So obviously starting here with the structure of the atoms, it appears as though the questions on the different STAR tests do not have pictures, as previously mentioned. So this is just, there for reference. Electron cloud, that would be this right here. This is where the electron cloud is where the orbitals are at. It contains the electrons. They are of negative charge and they have very little mass. And then you have the nucleus right here. That contains the protons, which have the positive charge, and the neutrons that have no charge. This is our periodic table. I would do a brain dump right now, but my brain doesn't work, so that's a shame. Moving on. Okay. So you have your two different acronyms, I guess. You have APE, which is atomic number, is equal to protons, which is equal to electrons. And that would mean that our 14 here, our atomic number, which is going to be this number up here, is equal to our number of protons. So we have 14 protons, and we have 14 electrons. Then we have mass, which would be right here, rounded, obviously, to 28. So 28 of our mass minus the atomic number of 14 gives us our neutrons, which is 14 neutrons. And that's how we're going to be calculating those different things. And moving on to the first question, which statement accurately describes the atoms of a specific element? F, an indium ion atom contains 115 protons, mistake there, inside the nucleus and 49 neutrons outside the nucleus. A scandium atom contains 45 electrons outside the nucleus and 21 neutrons inside the nucleus. An aluminum atom contains 27 electrons, 27 protons inside the nucleus. And J, a zinc atom contains 30 protons inside the nucleus and 30 electrons outside the nucleus. The answer here is J. We figure this out by, okay, so the atom contains 30 protons, 30 electrons. We know this because of APE, the first part, which means that our atomic number here, 30, is equal to our number of protons, which would mean that we have 30 protons and 30 electrons. So that's how we know that this one is right. Question number 2 of that same TEK. Which statement correctly describes the location and charge of the electrons in an atom cloud? And that is going to be J. The electrons are outside the nucleus and have a negative charge. We can see that here. They are not inside the nucleus. They are in the cloud surrounding the nucleus and do have a negative charge. May not be able to read it as well, but it is there. What is the total number of protons, neutrons, and electrons in a cadmium atom that has a total mass of, there's not meant to be a period there, 112. So, what we do for this one is, first we gotta do our APE here. So we find out the atomic number is 48, which means we have 48 protons, 48 electrons, which we are gonna move down here because we are trying to find the total, total number of protons, neutrons, and electrons. So we have 48 protons, 48 electrons, And then we have got to use our man, so our mass of 112 minus 48 is equal to 64. So we add those up and we get 160, making us, giving us the correct answer. What is the difference between the number of electrons in an atom of selenium and the number of electrons in an atom of aluminum? So to do that, we just, once again, use our A pair. Atomic number equal to protons equal to electrons, which means we have 34 and 13. 34 minus 13, 21. Bam. How many, yeah, we can skip this, we've already done this. Okay. Teak 8.5b, identify the protons, determine the element's identity, and valence electrons determine reactivity. If we look at our periodic table here, we'll see that we have these 8 columns shaded. These right here represent, what's that? Oh, okay. So this is like our, I gotta be quieter now. So this is our first column, right? These all have 1 valence electron. These have 2 valence electron. 3, 4, 5, 6, 7, 8. And we'll see here in a second when we add in the arrows. Along with the valence electrons, you also got your reactivity arrows. As we go down, you'll see that, You'll see that since there's more shells on the outside here, and these are trying to lose, so right they only have 1 electron on the outside. So their plan is to lose that electron, and in order to do so, they need to, well, you know, it's easier if it's very far away, because it's easier to pull it off. So that's why reactivity increases down here. And then over here with the 7s, they are trying to gain 1. So whenever the electron that they're trying to gain is closer to their nucleus, it's easier to grab it, making it more reactive towards the top of the periodic table. So element identity, every element has a different number of protons. If you change the number of protons, you change the element's identity. So protons equal identity, do not change the number of protons because that will change the element. Next up, our valence electrons here. So our valence electrons, those are our electrons in our outermost orbital. These are our orbitals, got our outside ones. We have 7 total electrons, valence electrons. They determine reactivity, and here we can see that 1 and 7 are the most reactive, 2 and 6 next most, 3 and 5 next most, 4 are just kind of meh, and then 8 are very unreactive because of their outer shell being completely full. And going back to the arrows thing, obviously, the more orbitals, easier to lose, more reactive. Less orbitals, easier to gain, more reactive. And we see that here. So obviously, this one right here, this electron would be harder to pull off than if we were trying to take an electron that was out here, farther away. Same thing goes over here. This one is going to be less reactive because it is harder for it to bring in new electrons than, let's say, a fluorine atom who has the electrons very close. Okay, moving on. Based on these drawings, which element is the least reactive? Okay. That is... Okay, wait, oh, what I did, okay, whatever, it's fine. Chemists made the table below to record some atomic properties of 4 elements. Based on the information in the table, which conclusion about the chemical reactivity of these elements is valid? It would be that fluorine is the most reactive because it has 7 electrons. If we go back to our other lists, we'll find that 1 and 7 are the most reactive because they really want to lose 1 or gain 1. And once again, valence electrons, reactivity. 4 students were asked to name the parts of an atom that determine the atom's identity and chemical properties. Students' responses are shown in the table below, which students' responses are correct. And that would be student number 2, who said that the protons are the identity, protons identity, protons identity. And chemical properties are controlled by the valence electrons. So, once again. A soft white metal has a low melting point compared with other metals. Tin is widely used as a coating for cans of food. Which statement accurately describes atoms of tin? Well, it would be that. I gotta think about this. So, tin does have 50 protons. It does not have 5 valence electrons because we see here that it is in the 4, the 14. If you just get rid of that one, I got a 4. So it does have 4, not 5. It does not have 119 neutrons. I don't want to do that math right now, but just trust me, it doesn't. Tin atoms have 68 electrons, and then we know that's obviously not true because of our ape. Teak 8.5c. Interpreting the arrangement of the periodic table, including groups and periods, to explain how properties are used to classify elements. So we have our groups here, our 1, 2, 3, 4, 5, 6, 7, and 8. And then with our transition metals in here, but we're not going to worry about those as those are not usually tested on. You'll see that these groups have very similar properties. They have the same number of valence electrons, so these all have 1, 2, 3, 4, 5, 6, 7, 8. And yeah, then we have our periods, which those are the horizontal ones, the ones that go like this. And those have the same number of orbitals / shells. Moving on, we see that our metalloids right here, we have these. There is a black line that goes right through here. And that right there identifies our metalloids. They're all going to be on that line, touching it. So phosphorus is not touching it, so it's not a metalloid. The only exception would be aluminum here, because aluminum is a metal, not a metalloid. To the right of our metalloids, we have our nonmetals, and then also including our hydrogen up here. It's just a little lost. And then all of these down here are our metals. All of this. So this question asks, how many valence electrons are in an atom of each element in group 15 in the periodic table? Well, that would obviously be 5. Just take away that 1, and we got a 5. So 1, 2, 3, 4, 5. Bam, 5 electrons. 5 valence electrons. Oops, I went too far. Yeah, they're probably, if the answer is, like, yeah, because this is an open-ended question, it probably won't be more than 8. Like, I really highly doubt it'll be more than 8. Skip on over here. For students, we're asked to complete a table for a science assignment. Which table was completed correctly? And we see here that this one is completed correctly. We have our non-metal in group 17. These are, yep, non-metals. And then we have in group 2, we have a metal. Yep, that sounds right. In group 1, our metal, rubidium, down here. Yep, that's a metal. And arsenic, which is a metalloid right there. And yes, group numbers are going to be up here, so the 17 would be the group number. Which pair of properties describes the elements in group 18? Okay, so if we go over to group 18, we'll find that those are our noble gases. This is probably going to be the only group that you would have to like memorize, know the name of, honestly. And just all you gotta know, 8 valence electrons, and that they're gases. That's very important. But yeah, throw back to the previous slide. 8 valence electrons, full outer shell, not reactive. And we'll find that the answer is, I think it's J. Yeah. Moving on to Teak 8.5d, recognize that chemical formulas are used to identify substances and determine the number of atoms of each element in chemical formulas containing subscripts. I know that's a bit blurry, but I was tired. So coefficients, those are going to be our big numbers. big numbers, coefficients. They tell you how many molecules there are, so like Miss Sylvia would say how many cookie packages you have. We find here that by multiplying the 2 times the 1, I don't know what atom that is, Ag, you get 2 Ag atoms in this thing, and then 2 times your nitrogen, you get 2 nitrogen atoms. 2 times your 3, because down here we have a subscript, the small numbers. They'll tell you how many atoms are in one molecule. So we multiply that 2 times the 3, and we get 6 oxygen atoms. And 1 is implied, obviously. Moving on, which chemical reaction involves the fused oxygen atoms? That's going to be J down here. We have our 3, our coefficient, times our 2 of subscript. Makes it have only 6 atoms of oxygen. That's the least one. Don't worry, you don't want to do the rest of the math. TEAC 8.5e, investigate how evidence of chemical reactions indicates the new substances with different properties are formed and how that relates to the law of conservation of mass. Very cool. So, evidence of chemical reactions, we have possible gases being produced, we have a temperature change, color change, precipitate being formed, or corrosion of some sort, as we can see here in this picture with this metal. So the question that has behind this, based on their observations, can the student correctly conclude that a chemical reaction occurred? And to that we say yes, because a new material of a different color formed on part of the metal strip. So that was not there before, and that's an indication. The solution is also lighter in color, so there was a color change. And we also have that precipitate and corrosion right there. Ish, sort of. This one's iffy, but you know, you get what I mean. Moving on to TEAC 7.5b. A student knows that interactions occur between matter and energy. The student is expected to diagram the flow of energy through living systems, including food chains, food webs, and energy pyramids. So, flow of energy, I couldn't find a really good chart for this one, but, you know, it starts with the sun, and it'll go down to your, not consumers, producers, and the energy will be ever decreasing as you go up, meaning that the higher you go, the more you gotta eat. So this badger gotta eat a lot. It's a fat badger. And our... Oh, okay. So yeah, that probably won't be on the test. I don't know, I couldn't find any of the past 3 STAR tests, so I'd assume it wouldn't be on there, but you know, people are weird. Instructional coaches. Moving on, TEAC 7.6a, the students know chemical properties, physical and chemical changes. Yep, I'm gonna just start reading that because we're on slide 54 and there's still like another 120 to go, so. Physical and chemical change. Physical does not change the chemical structure of the item, more irreversible than chemical, and yeah, so like ripping something or dissolving it does not, you know, it's still what it was. Ripping it does not, you know, if I take this paper and I just go, it doesn't, it's still paper. Chemical, if we change the chemical structure of it by, it's pretty irreversible, so burning something, you're not gonna just magically turn it back into some wood after it's already been burned. And also corrosion. And important, it forms a new material most of the time, or it does. We'll see here, chemical properties. I don't know, this is a weird question. I saw that they threw it in there one year and I was like, well, you know what, might as well go for it. So organic compounds, this is like from way back. They contain carbon. Yep, so that's why they're organic. They contain carbon, and they usually contain oxygen, hydrogen, and nitrogen, based on our little key here. And inorganic compounds, obviously the opposite here, do not contain carbon. Metals, nonmetals, and metalloids, physical properties. Okay, well, I think we, you know, mostly know this. So, metals are shiny, they conduct, they're pretty malleable, and they're typically solid, except for like mercury, but you know, mercury is weird. For nonmetals, we obviously have no shine, no conductivity, or low conductivity, low malleability, and then the state of nonmetals varies, as there is one of each state. Then you have your metalloids, which would they're all very dependent, and I'm pretty sure they're all solid. So that's something sure of, I think. Which statement does not correctly compare silicon with another element? Silicon conducts electricity as well as copper does. No, it does not. It's a metalloid. It's a metalloid, so that would mean that it does not conduct as well as copper. Oh, okay. Calculating density. So to calculate density, we use the density formula. This is included in your reference paper, I believe, for your STAR test. So density is equal to mass over volume. If we look here, if we're trying to find out what the density of these different items are, I'm pretty sure it's item 4, yeah. So 8.3 divided by the 3 centimeters cubed gives you your 2.71 grams per centimeter cubed of density, and that's exactly what we're looking for here. Teak 8.6, calculate unbalanced forces. So our force formula here is F is equal to, our force is equal to mass times acceleration. If we look here, we'll see that we got a mass and we have an acceleration right here. Just multiply the two together and we get negative 1,300 newtons of force. Moving on to Teak 8.6b, differentiate between speed, velocity, and acceleration. So speed is going to be your total distance over total time, so distance over time. It's going to tell you how fast, but it's not going to have a direction. If it includes a direction, then it's a velocity. So velocity is speed, but with direction. And then acceleration is the rate of change of velocity, so how quickly it's changing. This question, I think it was on one of our tests for Sylvie at some point, but essentially, essentially just, there's the math right there. They said 468 kilometers per minute, then we turn that into seconds by dividing it by 60. That gives us 7.8 kilometers per second. We found out that it was south to north direction, making it northbound. And that's how we got our little answer there. Moving on to Teak 8.6c, Newton's 3 laws of motion. We'll find that the first law is an object at rest stays at rest, and an object in motion stays in motion unless acted upon by an unbalanced force. The second law being a force is equal to mass times acceleration. And the third law, every action has an equal and opposite reaction. We'll see here in this question from 2018 STAR test that there's this person walking across a tightrope. It asks for which action-reaction pair exists here, and we'll find that it's the feet with the rope. The rope is pushing back, and then he's pushing down. So that's why that one's the third law. Moving on, potential and kinetic energy. We see here that high potential is going to be up here. So potential energy is that energy that is stored, not being used yet. It is typically influenced by the height. The higher up you go, the more potential you probably have. Kinetic is the energy of motion, so whenever you start going down the hill, whenever you start moving, that's when the kinetic energy comes in. It's the opposite of potential energy, so as potential energy decreases, kinetic will increase, and as kinetic decreases, then potential will increase. Then the little question that goes along with it, well, it's asking for where's the maximum kinetic energy. We'll find that that is right here, just before it starts going back up. That is going to be our maximum kinetic energy point, making it location Y. Calculating average speed. Okay. So So speed is equal to distance over time. We see here that it's asking for us to find the speed of this block being dragged. It says that it's 0.9 meters to the right in 2.5 seconds. So we just divide the 0.90 by the 2.5 seconds, and we get 0.36 meters per second as our speed. Moving on, TEAC 6.8D, measure and graph changes in motion. So this is going to be our little distance time graphs and other graphs. So on here, your distance is on the left, time is on the bottom. Straight lines mean no movement. So we see here that their distance is not changing. If it were changing, it'd either be going up or down, but it's not. It is staying exactly the same over time, which means that they are not moving. Do not get this confused with speed time graphs. No, do not do that, because a straight line on there is very different from a straight line on here. And then yeah, going up is getting farther away from your starting point, going down is getting closer. For our speed time graphs, we got our speed on our left, time on the bottom. Straight line means a constant speed. So right here, they're going 15 meters per second for 10 seconds here, meaning that they traveled like, I don't even know, 10 times 15, like 115. I don't know. I can't math right now, but you get what I mean. So straight line, constant speed on a speed time graph. Do not get that confused. And then those not like coming to a stop would be at the very bottom right here, where there would not be any speed. You'd just be there. So energy transformations now. So for energy transformation, this is just some good things to know, because I know that they've thrown these in there a couple times before. So batteries are chemical, food is chemical, heat is thermal, natural gas is chemical, and if it comes from the earth, it's probably chemical. We see here in this question that it's asking what the energy transformation is here. And as we find in our answer, it is that our chemical energy from the natural gas down here is turning into thermal, then heats the water, which pushes out some sound energy through the little sound or little thing here that makes a little whistle. And yeah, but really just look for something that's logical. If it doesn't make sense, like if it's going from some of the thermal energy and the natural gas transforms into sound energy when the water becomes hot, and then the sound energy changes to light, like where's the light in here? No. Just read the question. If it sounds dumb, it probably isn't right. Moving on to our next category, Earth and Space. TEAC 8.7a, tilted Earth axis causes day and night revolves around the sun, causing seasons. So we see here that Earth has a tilt of 23.5 degrees, causes day and night when combined with rotation. So as the Earth rotates, it spins, so every 24 hours. That gives us our day and night. And then seasons are caused by a revolution around the sun, which would be 1 year. And the tilt means that some parts of the Earth are further or closer during different times of the year. So the question here asks, why does autumn start in different months of the year in North America and South America? And we find that it is because of the Earth's tilt and the revolutionary period, because of, so meaning that it's not the same all the time. And that's why it's on different days for different parts, because they are in the south and they are in the north. Moving on to TEAC 8.7b, predict and sequence. Predict the sequence of events in the lunar cycle. We see here that we have our little lunar cycle with our sun on this side. It's always going to go counterclockwise. If the sun moves to here, then this is not going to stay the same. You got to move it with the sun. So you should always know that in front of the sun is going to be the new moon, directly across is the full moon, and if you're going to the left, it's probably waxing. Or at least from the, yeah, if you start on the new moon and you're going left, then it's waxing. Good things to know: moon orbit, the actual orbital, the actual orbit of the moon takes 27.3 days, but the lunar cycle itself takes 29.5 days. So it is important to make that distinction. There you go. There's your little list of lunar cycle. So we see here, which sequence of moon phases will the student observe over the next 8 days? And seeing that it's starting with full moon, our next would obviously be the waning gibbous, and the third quarter waning crescent. And we see that this A answers that, or A best matches that. Here we have a picture of the Earth with the sun on this side now. So instead of it, you know, starting right here and then going this way, it's starting right here and then going this way. And all we did to figure out what that moon phase was is just flip the picture around, and guess what? It's a waxing crescent, because what are we doing? We're going to the... Oh, I gotta think about it now. Going to like the right, the left, I don't even know, Chief. It's... Just know that it goes counterclockwise, whichever way counterclockwise is. I'm pretty sure it's left, but, you know. Kinda sleepy right now, so, you know, don't even try and, whatever. Okay, so it's waxing crescent, that's all you gotta know. But yeah, if the sun moves, you gotta move with the sun. Moon inside, ocean tides, so that you'll see that spring tides, we've talked about these before. Spring is full, it occurs during the full moon. Spring is full moon. You'll see that the sun and the moon, they're all pulling the same way. So when they're both together, they're really strong. It's like whenever you're trying to play tug of war, then someone joins in. It's easier because now there's another force also pulling this way. And that means that there's a large difference between the tides. Neap tide. Neap tide is the small one, so a little neap. It occurs during the first quarter and third quarter, and there's a very small difference between the tides, and you'll see that they form a little right triangle. They're adjacent, I think. Don't quote me on that. Okay. Moving on to TEAC 8.8a, components of the universe. So this was a question at some point, so I decided to throw it in there anyway. We find that stars begin as a nebula here, the stellar nebula. They either turn out normal, which would be an average star, or a bigger one. For normals, then continues on red giant, planetary nebula, and then a white dwarf. But if it is a massive one, it goes into red supergiant, supernova, black hole, or a neutron star. This one, okay. The pictures that they give you for the Hertzsprung-Russell diagram are in black and white for the star test. So what I recommend you learn is this right here. Left, hot. Right, cold. Up, big. Down, small. If you know that, then you can figure out just about anything. Because if we see here, the right is cooler, that means our red. And that if we go up, they get bigger. So we see that we have our giants here and then our super giants. That'll help us. So just memorizing these right here. Down is smaller. We see down here that at the bottom we have our white dwarfs. But also to the left, which is hotter, we also have, that's where the white dwarfs are at. Hot and small. And then main sequence just right down the middle. So the question asks which statement about the stars is correct, and that would be F. Star formation begins in a nebula. Just like we said earlier. Moving on, this is one of those pictures where we don't really have a color, so that's why I was saying to memorize it, and it's asking for where the white dwarfs. So if we remember that down is small, up is big, left is hot, and then right is cold, then we can find out that this right here is our small hot side. So that would make the answer D, area Z. Teak 8.8. This was kind of a pointless teak, but whatever. Just know that the sun is a medium star. We're in the Milky Way galaxy, and that the Earth is closer to the sun than any other star. But you know, I hope you know that, because if you don't know that, then I'm a little concerned. Electromagnetic spectrum is next at 8.8C teak. I know that we've done this one a couple times, but you know, just remembering that visible light is a very, very small part of all the different things. Got radio waves at your very longest wavelength, and then you have gamma rays at the very bottom, with infrared being more on the longer side, and then ultraviolet and X-rays being on the slightly shorter side. Moving on to the plate tectonic theory, we see here that we have our different little things. Plate tectonic theory basically says that the outer shell of the Earth is on several plates, and it's kind of just floating on the mantle. We have our divergent, where the plates are moving away from each other, and this forms a ridge. It lets out subducted crust. Convergent is where they collide towards each other. Usually one gets subducted, which puts the crust back into the mantle, and it usually forms volcanoes and mountains. And then we have our transform boundaries, which is where they slide next to each other. It causes some faults. See this picture here, it's asking what geological process probably created these mountains, and for that we would say plates converging, coming together, causing an uplift. Because as we saw earlier, it forms volcanoes and mountains. Moving on, topographic maps, erosion features, and weathering, all covered in teak 8.9C. You see that we have our little topographic map. Contour interval, that is going to be the amount that each one of these lines is worth. So we have 100, 120, 140, 160, 180, and then 200. So each one of these lines is worth 20 meters. That's basically all it's telling us. The lines that are closer together, this right here means it's really steep, because just think about it. You're climbing 1, 2, 3, 4, like 100 meters in this little tiny spot. So it goes from, you know, over here where you're climbing maybe like 1, 2, 3, 4. So the 100 meters, you know, is really spread out, or 100 meters really close together. So that's why that's steep. And X usually means a mountain peak is there, or something along the lines of that. So we see the question that goes along with this, and our answer would be A, because of the very steep side that's over here. It makes sort of a triangle shape. Moving on to teak 8.10A, the sun drives convection, producing winds. So we have here convection in the ocean. The way that this works is that the warm water is heated up here. It then travels to the poles where it gets cold. It sinks down, it mixes up, and then it starts coming back up after being a little bit warmed with some less cold water. Oh, oops, went back. It then rises, gets heated, moves back over, and then just begins the cycle all over again. Similarly for wind, the air is heated over here on the land, then goes up, it gets cold up here in the clouds, comes back down, then gets hot again, and it just keeps on going. we see here that there's a bit of a convection thing going on. Okay, there's convection going on here in this little beaker, it appears, and it's asking how that's similar to the ocean. And we say that the sun, or that our heat source is actually up here instead of down here, because we have our heat input to the ocean being the sun. Continuing on to 8.10b. How many more slides are there? Okay, we're close. Oh, oops. So, weather, high and low pressure fronts. Here we see that low pressure is brings warm, moist air, and that feeds the storms because it goes up and it makes a bunch of clouds and rain and no good. High pressure is where we have very cold, dry air and clear days, but I think it is high pressure, the one that whenever it collides with the warm, it does cause a line of thunderstorms to form. And high pressure, spiky. Low pressure, like circular, for the little signs. At least that's how it's usually going to be. So identifying the role of the oceans in the formation of the weather system. Oceans are very moist and warm, so they feed the storms. And that's what a hurricane is, just a big storm with a very low pressure. Next we have 7.8c, effects of the human activity on the watershed. So we see here that it's asking us, how does agriculture activity most likely affect the surface water of the area? And we said F because they're dumping fertilizer. Fertilizer makes things grow, and that's why we're saying that it's causing a growth in plants. But for these, once again, you can't. I don't think you can really prepare for these. You just gotta kind of be able to think about what makes sense and what doesn't, and then just put it together. Take 6.11b, gravity governs the motion of our solar system. Okay. So, oh, oops. Where'd it go? Okay. So, gravity is what, keeps our orbits elliptical. Keeps us from floating away, and obviously no gravity would be very bad. So, good job, gravity. So what keeps us from moving in straight lines? Gravity. Makes it elliptical. Elliptical meaning like oval-ish. Kind of. I don't know, wouldn't it be circular if it was like perfect, but it's not perfect. Okay, so biotic vectors and abiotic vectors. We see here that ecosystems depend on these factors, so biotic meaning living and abiotic meaning not living. Should be our rocks, water, sunlight, temperature, soil fertility. And I don't remember how this one exactly relates, but it just kind of does. So, sandpipers are the primary and secondary consumers here because they eat the grass directly, and then they also eat the grasshoppers, making them a primary too. Primary and secondary. I don't know what that was about, but whatever. Short, long-term environment changes affect organisms. So that's just talking about adaptation, survival of the fittest. So whoever's the best is gonna be able to continue on to reproduce. Leads to adapted organisms and better traits that are passed down to different generations. So it talks here about a shark that is kind of remaining still all day, and that it pumps water across their gills, and what that does is it gives it oxygen, and that's an adaptation there to allow it to be more stationary. This one right here talks about how some bacteria was not completely killed. You see here that it says almost all the bacteria were killed, meaning there was still some left over. Those probably not mutated, genetically mutated, I guess, to become more resistant to the drug that they were given. making the bacteria thingy come back, or what was it they had? Making the sickness come back. So biodiversity is next. For biodiversity, ecosystems obviously need to be biodiverse. That way, if one thing comes and wipes out all the pine trees, there's still a bunch of birch trees, and that's good. So variety means that it's harder to take them all down at once without it being too broad of an attack. And no diversity obviously means that one wipe and they're all gone. So it talks about here, makes it more sustainable by adding a greater variety of species, which allows it to adapt after changes occur. So further adaptation, and it protects the ecosystem. Next is TEAC 7.11a, it's economist keys. There wasn't much on the test about this, so I just kind of skipped it, but if you don't remember what one is, just follow down the list. Does it have fur? Does it have feathers? No feathers. Okay, we're going down here. External fertilization. Okay, then we go down here. No gills, and you go down here, and bam, you're there. Just follow the instructions, and you get there. Moving on, main functions of the system of the human organism. So that just talks about the different human body systems. We got our skeletal, keeps you from being a wad of jelly. Got your nervous system, which controls the body. Cardiovascular, which pumps blood. Respiratory, which lets you breathe. Digestive, absorbs the nutrients, breaks down food. Muscular, allows you to move. And endocrine, controls your hormones. There you go, there's your different body systems, excluding endocrine system. Next, we have our cell theory and asexual reproduction and sexual reproduction, genetic materials in the nucleus too. So this is all sort of review from 7th grade. You got your cell theory, which basically says that all living organisms are made up of one or more cells. They're the basic unit of life, and the cells can only be produced by the division of pre-existing cells. So cells just kind of like make more buddies, and that's how they reproduce, or are produced. Then it talks about asexual reproduction, and with asexual reproduction, it does not require a partner, and it produces almost identical offspring because it's basically just part of you. With sexual, it does require a partner, and it produces offspring with traits of both parents because of both of their genetic something being introduced. I don't know. Next, we have our organelles. You got your nucleus, which is the control center. A rough endoplasmic reticulum, which is the surface, which has a bunch of ribosomes. Smooth endoplasmic reticulum, which has this protein folding, but the mitochondria, the powerhouse of the cell. You got your chloroplast, which can control photosynthesis. The Golgi apparatus, which is the post office. Lysosomes, which contain enzymes, and then the vacuole, which is where you have your turgor pressure and water. And there's a little image of the of a cell, and here we see why that might be important. It asks us where is blood type stored. That would be a DNA thing, so we would find that in the nucleus, organelle number 1, right there. TEAC 6.12d says that basic requires us to know the basic characteristics of organisms, and for that I just honestly look it up because I didn't get that far. And that right there is our last TEAC. That concludes my reading of the 160 something slides. So I'll probably send out a link with the what do you call it, with the presentation. That way if y'all do want to look at that, then y'all can look at that. But yeah, that's gonna be all for now. I might do another one at 6 in the morning. Another reading. We'll see. But yeah. Good luck on your test.